Welcome to the morning session. So today we will begin a new set of lectures by Professor Soeren Schlichting, and he will talk about non-equilibrium dynamics on the lattice. So he has done very fundamental work on understanding and extending lattice techniques in non-equilibrium to address non-equilibrium problems, right from scalar field dynamics to understanding equilibration in heavy ion collisions. And he will share his insights in this set of lectures. And since this is a new topic of research, so please feel free to ask questions. Thanks.
Yeah. Okay, so yeah, let me start by thanking Sayantan Beck for this for putting up this great event here. It's really a great pleasure to be out in such a lovely place and extend this warm welcome to all of you. So I was asked to share a little bit of insight about possibilities to explore non-equilibrium QCD dynamics using lattice techniques. And so at the beginning when I was given this task, I was actually very confused on what I should talk about. So after thinking about this for a little bit, I decided that somehow, rather than showing you a lot of results and then somehow discussing a lot of QCD physics here, I would try to focus a little bit more on somehow the foundational aspects of what is going on and what actually motivates the use of these techniques and what somehow quantifies their range of validity. And so this lecture will perhaps be a little bit different than some of the other things that you have seen before, in the sense that I'll try to put forward a lot of formal development, but I nevertheless hope to give you some useful insights into somehow various techniques that are being used in non-equilibrium quantum field theory, and how they sort of compare to each other and what can actually be done. But so let's start with somehow why this is something that we should care about, and sort of give you a little bit of motivation for why we should be interested in studying quantum fields out of equilibrium. And so, of course, in the context of QCD, our primary motivation comes from the study of high energy heavy ion collisions, or heavy ion collision experiments in general. So, of course, as I guess everybody in this audience is familiar with, right? I mean, collisions of heavy nuclei are awesome in the sense that they give us this possibility to create a deconfined state of quark-Gluon matter, namely this Quark-Gluon Plasma. But as you can see at this cartoon here, which probably all of you have seen before as well, heavy ion collisions are also somehow highly dynamical systems. And so if you really just think about it from somehow a theorist's point of view, right, you start with a system which is somehow as simple as two atomic nuclei, right, and after a very short time, right, out comes this complicated mess that you see in the detector, right, where you have all these charged particles perhaps produced and so forth, right? And so really, as a theorist, this should pose you the question, is there actually any way that you can really understand this from first principles, from the underlying theory of quantum chromodynamics? Yeah? And so obviously, since this is a very dynamical system, right, we have to be able to deal with a description of quantum chromodynamics away from equilibrium. Now there's a second context, of course. I mean, there are many contexts where quantum fields appear out of equilibrium. But so the second example that is also known, I guess, to all of us, is our early universe. So this is a problem taken from cosmology. So here's a little bit of a cartoon indicating somehow the evolution of our early universe. And so here we have a very different, I mean, somehow the cartoon looks similar, so to say, right? But we have a very different scales of characterizing the space-time dynamics. And so just like a heavy ion collision expanding, our universe is also expanding, but it's expanding at a much lower rate. And so while in the late stages of this evolution of the universe, somehow the system has had somehow enough time to be reasonably close to equilibrium, such that we can typically treat it with near equilibrium methods, except for somehow perhaps some rare processes which are still out of equilibrium. The particular interest in this case derives from this very early stages over here, where early on we had this period of fast inflation, so accelerated expansion of the early universe. And there apparently the conditions were very different than what we're used to seeing nowadays, right? So nowadays our universe consists of matter and antimatter, right? Mostly matter. But early on somehow somehow the properties of the universe were very different. Now, of course, there we're talking about physics at very high scales, so we don't really know what the particle content is at these high scales. So in a sense, the problem is even more challenging than problems that we're facing in QCD, where at least we have somehow a well-defined starting point and we know the underlying theory of matter. But somehow the question that comes that comes into play here with regards to non-equilibrium physics is really to understand how matter as we know it, right, and how somehow the universe as we know it emerged from essentially a state where essentially the energy content of the universe was dominated by some inflaton field and quantum fluctuations. And so again, this is a far from equilibrium problem. So one of the surprising things that that actually turns out to be the case, and so this is why I kind of chose these two particular examples, is that they're actually more similar than you would think at a first sight. And so this regards both somehow the methods that we use in the theoretical description of these two systems, as well as the physical phenomena that we can observe in describing these two systems. And so throughout the course of these lectures, I'll be basically coming back and then sort of picking examples from either case and sort of compare them a little bit. Okay, so I think this sort of gives us enough motivation for why we want to study non-equilibrium quantum fields, right? We want to study them to describe heavy ion collisions, cosmology, or say maybe even cold atom experiments. So the question is, what can we do, right? And so perhaps the honest to God answer is actually we cannot do much. So non-equilibrium quantum field theory really is a somehow very difficult field, right? And the first thing I should point out is that really, if you want to study dynamics in an interacting quantum field theory, currently we don't know of an exact way to do that, right? So there's no truly first principle methods such as lattice QCD, which allows us to really study dynamics, non-equilibrium dynamics without further approximation. However, there is of course somehow a series of well-established non-equilibrium methods, and so if we want to study a given problem in non-equilibrium field theory, we have to choose somehow out of our potpourri of methods the method that we think is most suitable to describe the problem at hand. Okay? And so over here I've listed kind of a few of the methods that are currently known, let's say, and available to us. And so on the one hand, these are methods which are kind of based on microscopic descriptions. So these include, for example, semi-classical descriptions, which is actually a regime where we can, within classical theories, do first principle studies. And so a big part of these lectures will focus on somehow how to perform such studies and what is the kind of physics that can be addressed with these. There are also so-called real-time effective action techniques, kinetic theory. We'll also talk a little bit about these things. And finally, there's methods like holography. And I mean, this is not a complete list, right? So that will be, for instance, addressed, I think, in the next week's lecture by Johanna. So there are microscopic descriptions. So this will be somehow the focus of these lectures. And so having so many different methods at hand, right? So of course, the first thing you have to ask yourself is, what is their mutual range of validity, so forth. When can you use what methods, right? And so a big part of these lectures will somehow be dealing with, somehow what is the range of applicability of different non-equilibrium methods, and how can we use them to somehow study interesting phenomena. And so somehow before actually developing this whole theory behind this, right? I mean, what I should say is that clearly different methods have different ranges of validity, and so what turns out to actually often be the case is that a single method is not suitable to somehow describe the entire physics that you have, that you want to be able to study, right? And so you most of the time actually, if you want to tackle somehow a complex problem like a heavy ion collision, you actually have to use a combination of different non-equilibrium methods to be able to do so. Okay, so this then brings me kind of to the outline of my lecture. So here's a sort of a little bit of a list of what I'll be covering. So the most part of today, we'll somehow start with a rather basic introduction to somehow non-equilibrium quantum field theory and to how to properly actually formulate the problem that we want to be solving. I will then motivate the use of these real-time lattice techniques. So this is then really what I think came in the title, namely non-equilibrium QCD based on lattice techniques. And so once we've developed these techniques, we will then apply them to somehow study a number of non-equilibrium phenomena and the properties of thermalization of both scalar and gauge theory systems as they appear in cosmology and heavy ion collisions. And so there are some very interesting patterns emerging, which are somehow very generic and then sort of mutually the same between different theories. And so then towards the end of the lecture, I would actually like to come back and let's see if we get there, right? And somehow discuss some new directions in the field of non-equilibrium field theory, which are really working towards really getting to a first principles approach and actually being able to somehow get first principle insights into non-equilibrium problems. And so I should say, so far everybody seems to be quiet and paying attention here, right? But so yeah, I mean, I would rather not cover everything that I have prepared, right? But have you guys really understand what's going on? So please feel free to interrupt me at any time, ask questions, whatever. I even have rewards for questions if you want. Okay. So I put down some references down here. So most of this stuff I kind of just developed myself. So there's really not that many useful references out there. There's some nice lecture notes here by Jürgen Berges, which actually cover a great deal of what I'll be discussing there. And we also have sort of a review-like paper. You can see 45 pages here, which is written down there. I was perhaps a little bit sloppy on putting all the references on each and every slide, but the slides themselves are relatively detailed, as you will see. But please, if you want to have sort of additional literature or suggestions or so forth, please feel free to contact me either here in person or by email anytime, and I'll be happy to point you to somehow the relevant things. Okay, so let's get started. And so, as I said, somehow today we're going to start dealing with somehow the whole foundations of this of non-equilibrium quantum field theory, and first somehow make sure that we actually properly formulate the problem that we want to be talking about. Okay. And so, why are we going to do this? Well, the reason we're going to do this is because once we have formulated the problem, we can then sit down and see what are actually the levels of approximations that we have to make to be able to compute something. And so the one thing I really want to give away in this lecture is that I kind of want to point out what are some of the systematics between different approaches that I used in the field of non-equilibrium physics. Okay, so what is somehow our general question of interest? And so let's first start with an example from quantum mechanics. Okay, so this we should all be able to understand. And so generally the question that we want to ask is, we have a system which is prepared in some initial state at an initial time. This initial state in general will not be thermal equilibrium, right? And then what we want to do is we want to evolve the system in time and at some later time measure a certain operator. Okay? So how do we do this in quantum mechanics? Well, okay, if we choose, for instance, the Schrödinger picture, right, then this is the initial state is described by some initial state density matrix, right? Our operator is time independent, right? And so then the evolution of the system in quantum mechanics is governed by time evolution equation for the density matrix, which is the von Neumann equation, right? And so, okay, we can sort of formally solve that for time independent Hamiltonian, getting multiplications with the unitary evolution operator. And so then, okay, once we have properly evolved our density matrix, right, we can calculate any observable that we want, right, simply by tracing the density matrix with the observable of interest. Now, okay, so the first thing, so this is how we would proceed somehow in quantum mechanics, right? So the question is, why don't we do the same for quantum field theory? And okay, so there's a number of reasons why somehow this is not really practical, right? Well, first of all, I mean, to actually be able to perform this program, right, you have to deal with the construction of the Hilbert space and so forth, right? So this is, naturally, if you're thinking about gauge theories, this is perhaps not a problem that you necessarily want to tackle. But really the problem is that, I mean, in order to be able to actually calculate evolution of an operator, right, you have to deal with somehow the full size of the space, or the full large number of states involved, right? And so, as we know in the quantum field theory, these are infinitely many, right? And so somehow the exponential growth of the number of states with the size of the system is really what prohibits somehow the use of this. But this is essentially exact diagonalization, in the context of quantum field. So what can we do instead? Well, we still want to be calculating the same thing, right? And so the general strategy to somehow to avoid the use of the operator formalism in quantum field theory is instead to introduce path integral. Yes. So I'm considering. So I'm not considering a time-dependent Hamiltonian here. So typically, all the problems I want to be talking about is where the Hamiltonian itself is not time-dependent. No. So there's different types of. I mean, there's different types of ways you can set up a non-equilibrium system, right? So one of them, and that's perhaps what you have in mind, is you take an equilibrium system, right, and then you perturb it somehow. And that's usually done to some time-dependent Hamiltonian. What you would do there is you would take the Hamiltonian describing somehow just the usual evolution of your system, right? And you would introduce some additional operator with which you would perturb the system. Now here, the problem that I have in mind is different, right? I want to take a system which is not in a state of thermal equilibrium, right? But in a state, well, in a non-equilibrium state, right? But then I don't want to insert any external perturbation, so the system is just subject to somehow its own dynamics. That's described by static Hamiltonian. Okay, good. So let's carry on nevertheless. Right? Let's get derailed too much here by this construction, right? So of course the usual way to somehow to avoid the use of the operator formalism in quantum field theory, right, is to instead construct a path integral, right? And so I mean this is of course the same strategy you follow to somehow formally develop, say, theory of lattice QCD or so, right? I mean there you could also have written similar formulas to describe equilibrium states, right? But then it somehow turns out that the numerical evaluation of these things is just much easier done on the level of a path integral. And so the reason I'm kind of going through this is that this non-equilibrium path integral actually has some, well, let's say, if you're not used to it, perhaps rather peculiar properties. And so I'm just going to briefly go somehow through the construction and just to see what is the general structure of the things that is emerging. So to be concrete here, I'm just going to consider somehow relativistic 5 to the 4 theory, right? So that's action usual derivative terms, mass term, and quartic self-interaction. And so, okay, the object that we want to calculate is the expectation value of an operator, right, which in the Schrödinger picture is simply given by this expression that we had developed on the previous slide. Now, how do we do this? Well, the way we do this is we want to separate the problem, of course, into really its building blocks, which on the one hand correspond to somehow characterizing the properties of this initial state, characterize what time evolution does to the system, and characterize somehow the measurement of this operator, right? And so, okay, of course, this is easily done, right? So we insert somehow complete sets of states of the field operator somewhere between here the density matrix, right? And so in the first step between the density matrix here, and take the trace over the space, right? And so that separates us then, separates the initial state from everything that comes after, and then somehow repeating the same trick again, right? We can then insert another set of states essentially between these evolution operators and the observable measurement, and then somehow the other evolution operator and the observable measurement. And so we get this kind of factorized product. Yes? Very good question. So phi 0 plus, let's see. So phi 0 plus is the base. Okay. So phi 0 are eigenstates of the field operator, of the Schrödinger field operator, right? And so phi 0, so the insertion of this phi 0 plus here comes to the operation of taking the traces. Yeah. And the phi 0 minus is just an insertion of a 1. So just insertion of a complete set.
I mean, plus or minus sign, do they signify something, or it's?
No, we will see shortly what they signify. For the moment, they're just labeling the states. Yeah?
So, and in the first expression, why there is 2 extra, like phi f plus phi f minus? Are they just typos?
I made a mistake.
Yeah.
Yes, you're right. This should be crossed out.
Yeah.
Very good. I will correct this in the upper class. Please take a note of this. Thanks. Okay. Yes, they don't signify anything, right? So this is indeed the second insertion of the states over here. Okay, good. So now we have somehow bisected the problem into essentially 4 different parts. Is there a further question? No, okay. So we bisected the problem into 4 distinct parts, right? So properties of the initial state, one evolution here, measurement of the observable, and somehow another evolution. Okay, so okay, so this was essentially what I was saying, right? So looking at this structure a little bit more then, so what do we find, right? So, okay, we find that essentially the expectation of the observable is determined by 4 building blocks. On the one side, there's an initial state matrix element. So we take the matrix element. We are initially in a state phi plus state to start with. Then from the state phi plus, we have a time evolution going to a state phi f plus, okay? On that state, we act with the operator, which potentially can give us another state phi f minus, and then this state essentially evolves backwards in time to go back to the initial state. Okay? And so perhaps somehow more physical picture to think about how this thing is determined is if we consider if we don't consider the field basis, but we consider eigenstates of the density operator for the insertion of this initial state matrix element, and eigenstates of the observable, also of the operator O for the measurement out here. So what will happen then is that essentially both these matrix elements will be diagonal, right? And so in that case, right, the eigenstate, so in that case, the matrix element of the initial state can really be interpreted as the probability of finding the system in an initial state phi 0. Okay? Now, likewise, this will be likewise in the operator matrix element will be diagonal, right? And so, okay, so this will simply be diagonal matrix times the value of the observable there. So it's just the value of the observable in a particular quantum state phi f. And okay, since all the states are then the same, let me finish the thought here. What these matrix elements actually become, they actually become the square of a single matrix element. And so it's really nothing else than somehow the probability transition from an initial state phi 0 to a state phi f. And so really the reason that we have these kind of 4 building blocks is that we always have to essentially have a square matrix element, right, to give us, well, not the matrix element, but the probability from a transition from an initial state to a final state. Yes?
So why are you saying those metrics are going to be diagonal? I mean, I didn't get your argument.
So I'm using eigenstates of the density operator and eigenstates of the observable. Okay. Then they will be diagonal. Yeah. Right? So in that particular basis, you will have this diagonal structure. Okay, and so now there was the earlier question why am I labeling these states in this particular way? And so this has to do with a particular visualization of these matrix elements, which is called the Schwinger-Kelch. So sort of a nice pictorial picture of what we're doing here is, so what is going on, right? So we're starting from some initial state phi 0 plus, right? We're then evolving in time for some time to arrive at some state phi f plus, right? Which is the final state on what is called the plus or upper branch of the Schwinger-Kelch contour. That's where we perform our operator measurement, which will lead us to a different state, phi f minus, and that one we kind of evolve backward in time to arrive at a further initial state. And so you may ask yourself, so why is this? I mean, why is this so complicated, or why is this somehow different than, say, usual path integrals, or so that I may have seen in the study of quantum field theory or quantum mechanics, right? And so the reason is really that we are not imposing somehow here a particular constraint on what is happening in the final state, right? We're not saying, okay, we want to calculate whatever, say, E plus E minus 2 hadrons or something like this, right? We just want to say we have E plus E minus what happens. Okay, we're not somehow imposing any particular constraint on the final state, right? So essentially all final states here are possible here, and all of them will contribute to somehow our operator measurement. Yes? Excuse me?
Yes, sir.
So in the current context, this line actually extends to up to the time where we want to measure our operator. Yeah?
And this side, and phi 0 plus state?
That's at our initial time. Yeah? This is at our initial time where we prepare our system. Yeah? Okay. Okay, so this is okay. So now we have somehow factorized this problem into somehow its building blocks, right? But so we're still not in a position where we can calculate anything, right? So we still have all these operator present, right? So we have to carry on with somehow our construction of the path integral, and this then essentially, but now this essentially just follows somehow the standard construction of the path integral in quantum field theory, right? So namely, for each of these transition matrix elements, which appear once in the amplitude and once in the complex conjugate amplitude, so once for forward evolution, once for backward evolution, we can then essentially carry out the standard standard construction of the path integral, right? And so what this matrix element will become on this construction is just a path integral where each path is weighted by classical action in a way that the path starts at the initial state phi 0 and ends at the initial state at the final state phi f plus, right? So visually, right, so we start at this state here, right? We end at this state here, and we have to somehow perform an average over all possible paths in between, right? Weighted by their action, but with an imaginary phase factor. Okay, so this is for the matrix element in the amplitude, right? So similarly, the matrix element in the complex conjugate amplitude will be obtained by complex conjugation, right? And so that essentially completes our derivation of this non-equilibrium path integral, which then actually nicely factorizes into somehow these three buildings. So on the one hand, we have our initial state matrix element, we have our measurement, and so these are necessarily given to operators, right? Because, okay, we have to specify the operator that we want to measure, right? And we have to specify the density matrix that we put in, right? There's just no way around it, right? Yeah. But then for somehow the part that we actually kind of care about, namely what is actually describing the non-equilibrium dynamics, right? We have then expressed this through this path integral, which actually turns out, so because we have the evolution in the amplitude and the complex conjugate amplitude, to involve essentially the difference of actions between the forward-going branch and the backward-going branch of the Schwinger-Keldysh contour with this imaginary phase factor IH bar. Okay. So then now, so this was somehow constructed for this example of quantum mechanics, right, or the measurement of a particular operator, so to say, right? But so okay, I mean, generically, when we want to somehow study non-equilibrium system, right, we don't set out and say, okay, I want to study this particular operator after this particular done, right? You kind of want to keep some freedom, right, to measure whatever your operator you want after a given amount of time that you have evolved the system, right? Because that's really what will somehow characterize this thing. And I mean, oftentimes actually, so as a practitioner of this non-equilibrium dynamics, right? So oftentimes when you kind of start looking at these problems, you don't really know what's actually the thing you want to be looking at the end, right? So oftentimes, you kind of just start to discover some interesting features, and then later on you kind of realize, okay, this is really what you should be looking at, and that's how you can somehow understand the non-equilibrium physics, right? Yes, there was a question.
So in the previous slide, so this non-equilibrium dynamics, like the action in the forward direction, action in the backward direction, is it like sort of like irreversibility in the system? I mean, causing irreversibility sort of thing?
So at the level that I've been discussing, so at the level that I've been discussing this problem so far, right, we only have unitary time evolution, right? And so unitary time evolution by definition is reversible, right? So the reason that this, I mean, the reason that this difference appears is simply because calculate expectation values, right? You have to have sort of an amplitude and the complex conjugate amplitude, right? And so as you can see, right, this backward going path, right, is essentially just the complex conjugate of the forward going path because you have this I.
And the reason I'm asking is, like your associate, like every path is weighted by this classical action, just as we do in like normal stat mech. I mean, how valid is this? I mean, weighting factor, and we're just associating with each path this classic like exponential of IS weight. So I mean, I'm just little. I mean, how is it making different from equilibrium thing?
So if you okay, so what do you want to okay?
Like the way we are weighting paths in path integrals, like exponential of IS, or even in stat mech we like weight like exponential of minus beta.
Exactly, and that's exactly the difference, right? So if you wanna visualize this in the complex time plane, right? So what you do, so this is the sum of the complex time, right? And so what we do in non-equilibrium field theory, right, is we somehow have an initial state here which is characterized to its matrix elements, right? And then we kind of go in real time forward, right? And then we come back, right? And so in principle there's a sort of a infinitesimal tilt of the contour here to make the integrals convergent, right? So this kind of has a slope I epsilon here, going in the imaginary time axis. But we're evolving forward in real time. Now for bosonic quantum fields in equilibrium, what you do is you basically let's do it separately, right? You start from a certain state, you evolve in imaginary time, right? And then you have essentially sort of a periodic identification here. So the construction is exactly the same, except that it's evolving in real time, you're evolving in imaginary time. And there's no need to go back because after going a distance which is beta, right, you automatically have periodicity. In this case, you want to connect sort of different possibilities of initial states, right? And that's why you have to go forward and then come back. Yeah. Okay. More questions? Yes.
How does that part describe the non-equilibrium dynamics?
So I mean, this part is, I mean, so as you can see here, right? So we had these 4 building blocks, right, which came from the operator measurement, right, the initial state, and the evolution in between, right? And so as you see, right, what the evolution in between, right? That's just like a standard, like a standard construction of the path integral, right? Like you do in, I mean, you can find this in any textbook, I guess, right? And I mean, that's exactly what's giving rise to these action, to these action phases here, right? So that's what's somehow connecting. I mean, other way to say this on this picture, that's what's connecting the states at 0 with the states after some time t, right? And okay, what's going on in between is the non-equilibrium dynamics, right? I mean, which part are you worried? Are you worried about? Are you worried about equilibrium or non-equilibrium or dynamics?
Yeah, non-equilibrium.
Okay, yeah, no, it could also be equilibrium dynamics, right? Because I haven't said anything about that. I mean, it's just dynamics, right? Yeah.
Yeah, the definition is fine. I mean, you start with a non-equilibrium system. That is why it is describing the non-equilibrium dynamics.
Exactly, yeah. I mean, you could also start with an equilibrium system, for instance, right? In which case you could actually combine these 2 descriptions. So in that case, you could actually you could now also basically perform a path integral construction for this initial state, right? And you would end up with a contour which would look something like this, where you first go in real time, say, come back, right? Then you evolve in imaginary time, and at the end of the thing. So let's carry on, unless there are further questions. Yes?
We have here. So can I stop it? And so if when you take a turn back, in the real time you go and then you take I epsilon and then you come back. Can I truncate my contour at some other point t? So if I have t0, I t0 prime.
excellent question. Excellent question. So generally, what you can do. So let's redraw the contour. Okay. So this is our contour, right? And so generally, the contour has to run up to the latest time of interest where you want to measure something. So it runs up to some time t max. In principle, you could extend it further. So say, okay, basically what that would amount to is essentially inserting further evolution after your latest operator measurement. But basically what that would mean is you would just basically add some, you would insert something like e to the plus IHT for somehow going an additional forward, and then e to the minus IHT for going additionally backward again, right? And so as you can see, this is equal to 1, right? So this part basically then cancels out. So if you have a maximum time of interest for which you want to measure an operator, right, then there's no need to somehow extend the definition beyond that, right? Because all it would give is unity. Okay, more questions? Yes.
Prepared and you have given the initial conditions. Now it will evolve in the forward direction, right? So is it actually coming backward, or it's just the...
It's just something we have to do. I mean, it's just something we have to do in quantum mechanical systems, right? Because we have to essentially evolve the system, if you want to, in the amplitude and in the complex conjugate amplitude, to somehow actually get the probability at the end of the day.
Yeah, but once I
mean, the system, of course, the system only evolves forward in time, right? I mean,
yeah.
Like I'm standing here, I'm evolving forward in time, right?
Yeah, that's what I'm asking. Is it actually coming back, or it's the...
No. I mean, it's a trick essentially we do in the mathematical formulation.
Okay, thank you.
Actually coming back. You want to ask something or comment? Okay. Good. Okay, so let's so let's carry on further. Okay, so
how that measurement originated from what particular path is irrelevant from the quantum mechanical point of view. So this perspective that we are evolving forward is somehow a classical perspective. Right? So I mean, in quantum mechanics, you do measurements at various points, say, right, and you construct operators. And that's the only meaningful thing you can say. What are the paths that led to that particular measurement?
Absolutely, yeah.
Could be backward paths, forward paths around the moon, right? I mean, it could be anything, right?
Yeah,
so,
no, absolutely.
Sense, yeah.
Right. I meant it in the system. If you consider the system as your density matrix or something like this, right? You would think of the density matrix as just being a single-valued function of time, essentially, right? Yeah. And okay, at a given time, you can chop an operator, right? It's not that you. Okay, but good. So let's carry on a little further, right? So now we have constructed somehow this beast for measurement of a particular operator. I think we more or less understand the structure that it's giving to us. But so in general, okay, we don't necessarily want to focus on one particular operator, right? We want to somehow keep the freedom to measure all the possible operators that we can. And so the usual trick how we do this is that instead of considering a particular operator, we actually consider a generating functional, which then allows us to essentially obtain every possible operator that we want to measure. Right? And so the way we have to do this for non-equilibrium systems. So let's perhaps go back to what we had for the measurement of the particular operator. Okay, right. So what we had for the measurement of the particular operator was essentially the initial density matrix, and then this. So this is a Schrödinger operator. This combination here together is actually a Heisenberg operator, at that particular time. And so now, instead of considering one particular operator there, what we consider is a contour time ordered, and I'm going to say in a second what that is, contour time ordered product of the exponential of the Heisenberg field operator coupled to a source field, J. And so for later convenience, in addition to somehow having this one-point source over here, right, I'm also going to introduce two-point source, which then doesn't couple to one Heisenberg field operator of the field, but it's at two of them. Okay, so that's just, so this part you can forget about for the moment, right? It's not, perhaps not terribly important, but so this and so this then acts as a generating functional for correlation functions. So namely, right, so I mean, how would I now obtain, say, the expectation value of my field? Well, I can do a functional differentiation with respect to the source here, right? That would bring down the field operator from the exponential, right? And that would, for instance, allow me then to measure the expectation value of the field. Okay, now there's something to be said about here, this contour or this contour time ordering, right? And so this comes back to your question, what is somehow the maximal time that we want to go to, right? And so generally, okay, we want to keep the freedom to explore all times, right? So we somehow send the end of our path all the way to infinity, right? But we still have to come back. And so in order to somehow perform the same steps of the constructions of the path integral, right, essentially what's important is that if I insert some operators here, right, along my path, it's important that somehow the ordering of operators somehow follows the ordering of the path, right, such that in between I can always use the usual construction of I mean, I can construct the transition element and write them as the usual path integral, right? And so this is why for this generating functional we have this so-called contour time ordering, which means that the operators are ordered sort of starting from here, and then as we go around, we go back here, right? So the earliest time on the path is here, okay? And the latest time under this ordering is as we just come back to the initial state. Okay? And so this then essentially allows us to somehow write everything that we've done so far in a very compact form. So what still remains is somehow this initial state that we will never get rid of, right? Simply because different physical initial states will do different things, right? But all the rest of this non-equilibrium generating functional is then encapsulated in this non-equilibrium path integral over here, which now simply goes from a given initial state phi 0 plus to the initial state in the complex conjugate amplitude phi 0 minus. And so in between we have this difference of the action of the classical action factor. So this contour action is actually the difference of the action between the upper and the lower path. But we also have the coupling to our source fields, which we can then use to derive, for instance, correlation functions or any other operator that we want to measure. Okay. Questions? Yes.
So in path integral, since we can go in any path at all, the path ordering ensures that it will follow the particular path. It will not come back to a particular point twice or.
No, okay. So I think you're having a little bit of a confusion here. So there's path ordering, right, which has nothing. Okay. So there's the path integral and there's path ordering, right? And so these are, I mean, these are distinct things, right? So how do I? So what was the question again?
Path ordering, do you mean that it cannot come back to a particular point twice?
No. So what I mean by this, right? So the fields that are written up, they are operators, right? So these are Heisenberg field operators, right? As I denote here by the subscript H, right? And so the point is, okay, so I'm now inserting a bunch of operators instead of just inserting one, say, right? So say I insert 3 operators here, right? And I insert an operator here, and then I insert an operator here, and I insert an operator here. Then quantum mechanically it makes a difference in which order I write them, right? So let's call them somehow phi 1, phi 2, phi 3, right? Then in quantum mechanics, phi 3, phi 1, phi 2, say, right, is a different object than if I permute them. What I'm saying is that in order to be able to construct this path integral, they have to satisfy a particular ordering, and the particular ordering that they have to satisfy is that they're ordered as I move along the path, okay? And so what this means is that, so I move along the path here, so I have to put phi 1 here, phi 2 here, and phi 3 here, because This is how the system works. Okay?
So it is the ordering of the operators.
So it's ordering of the operator, right? Good. Okay, so yeah. Okay, so in principle, I mean, this is the object of non-equilibrium quantum field theory, right? So in principle, this is all I ever have to compute. If I can compute this object, I'm done. I have solved every problem in non-equilibrium field theory exactly. So the question is then, how can I actually calculate? Okay, and so that's essentially the question that we'll now be dealing with throughout the rest of these lectures. And so how do we evaluate? Well, so the first thing that this week actually, right? You guys have had a bunch of lattice lectures, right? And so the first thing that may come to mind is perhaps, well, maybe we can somehow use the same techniques, right? And just do sort of an importance sampling Monte Carlo. There's a problem with that. And well, anybody sees the problem? Well, it's written on the slide. So I'll just say it. Too bad, I should have asked this as a question. And so the problem is, it really comes from this weighting of these different paths. So the weight of each path here is somehow purely imaginary, right? And so what that means is that really what is somehow contributing to this path integral is somehow, interferences between all these possible ways that the system can take, somehow connecting one state to the other, right? And so if I were to just somehow randomly throw configurations saying, okay, these are somehow paths, right? They would all contribute with oscillatory weights, and I mean this would be impossible to evaluate numerically. So somehow a direct numerical evaluation is essentially impossible due to this severe sign problem. Although there are some ideas actually how these kind of problems can be tackled, and that's actually what I want to come back to at the very end of this. Yeah?
I have a question. So till now, this path integral is not different that we wrote in normal in quantum field theory, say for 5-4 theory. The way you have written the path integral, it is not different from the normal way that we are introduced to.
No, absolutely not. I mean, the only difference is that usually what you consider, right? Usually what you consider in, say, your quantum field theory classes or so, is you consider scattering problems. Right? And so scattering problems, you have essentially some state phi 0 and some state phi f, right? And what you want to calculate is just the matrix element between these states, right? Now, the difference here is I don't specify which state I want to end up in, right? And so I essentially have to sum over all possible states in the final state, and that's essentially what's forcing me to go back. Moreover, the initial state may not be a pure state, but a density matrix, and then I have another state. Yeah? Other than that, that's the full story. Yeah? It's the same story. Yeah, but so to somehow, appreciate these differences, this is why I kind of went a little bit through what is going in there. Okay, so we cannot somehow, or hardly, let's say, well, actually for quantum field theory it's impossible, cannot evaluate this thing in its full glory, right? And so what can we do instead, right? I mean, we still want to learn something about, non-equilibrium quantum fields, right? And okay, so, I mean, if you cannot solve a problem exactly, right, what you try to do is you try to find an approximate solution, right? And so what we somehow need to do is we need to find suitable approximations based on expansion, ideally in a parameter that is small. Now, okay, there's no free lunch. Usually there are oftentimes there are no small parameters, but okay, we should nevertheless explore what we are able to do, right? And by somehow studying the properties of this expansion, we will also learn about, what are their corrections. And so there are essentially two types of expansions that I will explore in the course of these lectures. And so the one is on the one hand the semi-classical expansion, which you can formally see as an expansion in H bar, although that's not terribly useful when somehow quantifying corrections to these expansions. And the other thing that you can, of course, think about is to say, for instance, do a weak coupling expansion. You could also think about strong coupling expansions in principle, but this is somewhat more tricky, let's say. Okay, so what we're going to explore today is expansions in H bar, and so we expect recover if I expand in h bar. Classical plus some perturbation. Exactly. So what we expect to cover if we expand in h bar, right, is somehow classical field, right? And so in order to somehow get a feeling for where this journey is going, right, let's first think about what would actually happen. Right? So in quantum field theory, right, so for each somehow initial state and final state, we have to, in the amplitude and conjugate amplitude, right, we have to somehow go through all these different paths, right, and each path will contribute with a different phase. Okay? Now, if we compare this with the evolution that somehow a classical theory would do, right, then, okay, in a classical theory, right, I would start with, say, some state of fields, right, so, okay, I have some profiles of wiggling fields, right, there would be a classical equation of motion of the fields, right, which is obtained by extremizing the classical action, right, so this would be the equation of the motion of the scalar fields, okay, and that gives us not somehow an incoherent sum of different trajectories, but it gives us one unique trajectory connecting an initial state and a final state, okay? And so somehow what has to happen in this simplification or in this expansion is essentially that, you know, somehow these incoherent weights of all these paths essentially largely cancel out in a sense, right, and just reduce to contributions of a single. So let's see how this works. And so it turns out that actually to somehow work out the classical features of this non-equilibrium path integral is really not that, it's actually not that straightforward to do. Yeah? And namely because you have somehow these two different paths, right? And you don't a priori know how to connect this with somehow a classical thing, right? Where really in a classical theory, you're really just going forward in time, right? You start here, you have an initial state, you have a final state, and you have essentially, you don't have an amplitude, the concept of an amplitude and a conjugate amplitude, you just have evolution forward in time. And so the way this works, and this is, by the way, there's a nice paper which kind of works this out in great detail, is that to somehow isolate the classical features that appear in this non-equilibrium path integral, what you have to do is you have to actually do a change of basis where instead of somehow talking about the fields on the upper branch of the contour and on the lower branch of this contour, you talk about somehow the average fields between the two contours, which is what I'm going to call this phi here, and the difference of the fields between the upper and the lower branch of the contour. And so it makes sense actually to normalize these by an inverse factor of h pi. Okay, so what we're interested in is somehow what is happening with this difference of the two actions. And so what happens under this difference of actions is that, okay, so now you have to essentially, oh, this is a typo. This is a bad typo. So let me do this on the board here. So we have the difference of the actions between the upper and the lower branches of the contour, right? So what we have to evaluate is something like s of phi plus minus s of phi minus, right? And so under this change of variables, what this becomes is it becomes s of phi plus h bar over 2 times, so phi is the average field, and this is the difference field, right? Minus s of phi minus h bar over 2 times the difference field. So this is the field on the lower branch of the contour, and this is the field on the upper branch of the contour. Now, okay, for all we know, right, we can now expand essentially the action around this classical field phi, right? And so what you will see is that, okay, so at leading order, so only the odd parts in the expansion will contribute, and so kind of the leading term that you get is something like h bar times the st phi evaluated on the classical fields, plus some higher order terms, okay? And so I've written this down here, so this is supposed to read phi plus minus phi minus, okay, obviously. And so indeed what you get is the first part that you get, that is essentially what I've written here, h bar times the st phi. So the h bar that you get cancels with the 1 over h bar that you have up front. And so you get a path which is linearly proportional to this difference field, multiplying actually the classical equation of motion. Okay? Then you carry this on further, right? So you carry this on further, you will, as I said, all the odd parts in the power series will contribute, right? And so the next part that you pick up is a quantum what one should call a quantum correction, right? Because it's nothing to do with the classical equation of motion. And so what you find is that, so it's proportional to this quantum field psi to the third power times the field phi. Okay, the classical, I mean, the average field phi, and so that's a quantum correction, and that comes with a relative prefactor of order h bar squared. Okay, and then so if you actually work this out carefully, right, so to somehow write the classical equation of motion in this way, what you will see is that you will actually generate two additional boundary terms, which both live at this boundary of 0, simply because that's where the path has its boundary. So this takes about, I don't know, 3 lines or so to work it out. If you're interested, you can either, I'm sure you can actually work it out yourself, or you can look at this paper to somehow work this out. Okay, so now what does this mean? Right? So now putting somehow these things together, we can now replace what we had here for the path integral, and we can express this in this new basis. And so what one finds is that the part that's related to the non-equilibrium dynamics simply contains now this classical contribution and its order h bar squared quantum corrections, right? And so somehow these initials, so these additional phases that one obtained from the boundary, they actually absorbed. They only live on the boundary, right? So they should be somehow reabsorbed into what we call our initial states and our operator measures. And so, as it turns out, actually, what the role of these boundary terms is that they somehow characterize essentially how off-diagonal your, say, for instance, initial state matrix elements are. So really, what they are is they are kind of a Fourier transform of the density matrix elements, right, which somehow has the initial field state, right, but also so the initial phi state, but also this psi naught, right, and so it's essentially a Fourier transform with respect to this difference between the right and left state, the right and left-handed matrix elements of the density matrix, and so these objects, they have a name actually, so they're known as Wigner functions, quantum Wigner functions. And essentially what they do is they kind of characterize, if you want, so quantum mechanical phase space measures. So there's a whole formalism which is known as Wigner-Weil quantization actually, which aims at sort of a phase space description of quantum mechanics. And so there these kind of objects appear all the time, and so they're really just phase space representations of quantum mechanical operators. So really what you should think of this object over here is somehow a representation of the density matrix, now not as an operator, but as an object which actually lives on the phase space, namely the phase space of the initial field and the time derivative. Okay? So this is what somehow happens with the initial state and final state matrix elements, right? But okay, so I mean, these were not the most complicated parts, right? The most complicated parts were which were somehow associated with the non-equilibrium dynamics, right? But now what we see is that if we expand the part that's associated with the dynamics to leading order in h bar, and the corrections are here actually of order h bar squared, then what you will see is that, okay, this field psi actually only appears linearly in this functional integral, right? And so it therefore acts just as a sort of as a constraint field, if you want so, and I can integrate over it. So now performing the functional integration over this psi field, essentially what I will get is I will get the delta function of this expression over here, right? But this expression is really nothing than the classical equation of motion, right? So after performing this integration, right, and somehow just rewriting these objects in terms of what they actually are, namely these Wigner functions, so these phase-space representations of quantum mechanical operators, what I end up with is an expression which is something like this, where I'm still integrating over initial and final field states, given by the phase-space measure, phase-space distributions, if you want so. But now I have a delta function, right, where essentially only the path where this average field between forward and backward going branch satisfies the classical equations of motion is inside the delta function, meaning that only the classical paths actually contribute. Okay? And so, as I said, the first correction to this expression is now of order h bar squared. Okay, so now this is something that I can actually calculate, right? Because this is now actually classical field. Right? So now for each particular initial condition, which will be characterized by some initial field and its initial time derivative, right? I have to follow classical equations of motion until the time when I want to measure some operator, right? And then simply evaluate that operator over here. And so, okay, this is actually what I had on this slide. Wonderful. So how do we evaluate this formula? Well, it's very simple, right? So okay, we have to start. So we have to start with some initial field, right, which is given by phi 0, right? Its time derivative, which is given by some canonical momentum pi 0, right? Then we have to solve the classical field equations, which will generate us these classical trajectories. And so I will denote this as sort of phi classical, so the classical field evolved from these initial conditions. Then I can go calculate any observable that I want by evaluating its Wigner transform. And so typically, actually, I mean, for the simplest operators, like any power of the field, right? The Wigner transform is actually just the operator itself. So most of the times, these Wigner functions are actually sort of overkill. They're actually simpler than they may appear like in the first place. But there are examples also where actually the notion of the Wigner function is extremely important, and I'll come back. Okay, so once I know these classical trajectories, I have to then calculate the observables from the classical trajectory. And now this is an important point, actually, and this is why this is not called classical field theory, but classical statistical field theory. I still have to somehow perform a statistical averaging over the different initial conditions, which given, I mean, with their initial weight as specified by the Wigner. And so, so this is somehow the footnote that's down here, even though somehow the field evolution in this case is actually classical in the sense that for each member of the ensemble, right, I follow classical trajectories, they are actually still there's still quantum information encoded, or can be encoded, in these Wigner functions. And that's in principle the case both for the initial state as well as for the observable that I measured. Questions here? Yes.
One thing which I just want to understand if I got it correctly, the demand that we have a C plus and C minus contour beginning and ending at the same point. So you go from t equal to 0 to TF, and then from TF it comes back to T0. It's only because you have square of the matrix amplitude, right?
But basically,
I mean, I go in C plus from T0 to TF and don't come from TF to some T prime back. I come exactly to the state, which is...
I mean, it's just rewriting these...
right.
So here, I mean, so far we've just inserted complete states, right? And then it's just, it's just inserting, this is TF, right?
Right, so it's just the requirement that I have a complex conjugate. That's nothing.
Exactly, right.
It's just that.
Rewriting the complex conjugate amplitude by a backward going path. More questions?
Why the corrections is only up to order of h line square? Why, when there is no correction order of h line? So, is that how maths follows, or there is some other reasons?
Is that what?
The corrections you are talking about in that operator. So it starts from h line square.
Yeah.
H bar square.
Yes.
So there is no corrections of H line. So is there any physical significance?
Is there physical significance?
Or-
Works
Or
out
it's
that
just the
way.
maths, or just like there is some issue, like yeah, H line bar should not be there.
So if there's okay, I mean, let's be very careful here, actually, okay? So there's three pieces to the final answer, okay? And they come with different, I mean, so corrections can be of different powers in H bar. So in principle, so with regards to this this non-equilibrium dynamics, so the part of the integral that really characterizes the dynamics, right? There the corrections are really of order H bar squared. Now, if there's a deep reason for this, at least I'm not aware of this, right? It just comes out, but there's many different ways that you can actually look at this, and irrespective of it. So again, one very powerful way to find this actually is this Wigner-Weil formalism, where you basically replace the Poisson bracket by something that's called the Moyal bracket, and you also find that it's of order H bar squared. So this is so with respect to the dynamics, it's really of order H bar squared.
Okay.
And I'm not aware of a deep reason. Now, there are these two other objects here, right? Like the Wigner function and actually the Wigner-Weil transform of the observable. And these in principle can have order H bar corrections. But the order H bar corrections of these can actually still be treated semi-classical. That's somehow the appeal of this. So actually to order H bar, everything can be described classical, semi-classical. Can you pass the microphone?
Why do you want to perform the statistical average?
So, well, I mean, you have to. I don't want to. I have to, right? I mean, the reason I have to is that I still have these integrals over here, right? So I still have to integrate over the possible initial state and the possible, in this case, the possible final state. What you do in practice actually is you map the integration for a final. So this is like a shooting problem, right? You have a field configuration here and you have a field configuration here, and you want to see how to come there along a classical path. But you know that since classical paths are unique, right, you can map this to an integration over an initial field and an initial time derivative of the field, essentially. So you have to integrate simply because you still have these integrals left here. And this is precisely the difference between sort of a Wigner function, right? So the statistical, Wigner function is also not positive definite necessarily, but somehow statistical distribution of states, versus having an exactly known classical field configuration. So you still have to integrate over somehow the possible initial field configurations as characterized by the Wigner transform of your density matrix.
Not starting with some particular initial conditions, it's a set of initial conditions.
Exactly, you have to perform it. So in order to characterize, so in order to correctly represent somehow statistical nature of the system, of the quantum system, right? You have to map this to an ensemble of classical fields. A single classical field configuration will not be sufficient to somehow really signify this. You're always left with an ensemble of classical fields, precisely due to the appearance of this.
So, I mean, what intuitively comes to your mind when you do statistical averaging is that, are you looking at some kind of a thermodynamics in the system? But essentially you might not be, because it's a non-equilibrium system. So, I mean, how does one entangle this?
No, it's just an averaging over essentially different configurations of the classical fields at the initial time, right? But they may be given by whatever the properties of your non-equilibrium state are, right? If you want to study an equilibrium system, these would actually be equilibrium configurations.
So it all depends on the initial conditions that you are starting with.
Absolutely. So what exactly, right? So what you have to throw in as your initial conditions, right, depends on the properties of your initial density matrix, or rather its Wigner function. And that's in principle something you have to calculate or specify, or is determined by the kind of experiment you do, right? Or however it turns out. Okay. Yes. Okay. So yes. Where? How?
So, what is the form of the density matrix? Like in Wigner function, you have.
Well, that I mean that's precisely the same question, right? It depends. I mean, it depends on the problem how you set up your system, right? So for each particular example that I'm going to discuss here, I'm going to tell you what the initial conditions are. Okay.
Okay, thank you.
So it turns out, actually, yeah. So let's go a little bit ahead, maybe, yeah. That for a lot of the interests, okay. So we're studying somehow non-equilibrium many-body physics, right? And so it turns out that for a lot of the interesting physics that you can look at, yeah. If you look at very short times, you'll basically see your initial conditions, and it will sort of strongly depend what the details of the initial conditions are. But typically what happens is that these non-equilibrium systems, they rather quickly forget about somehow the details of the initial condition, and they really show generic features of the non-equilibrium evolution. So for a lot of the things that we'll be discussing throughout this course is actually the details of the initial state will be almost irrelevant.
If they don't consider, if they forget the detailings of the initial condition, then there should be like one possible choice that will work for all the cases, like cold atom or heavy ion collision.
I mean, you have different. I mean, clearly you have different fields, right? So there's different aspects that come into play.
Okay.
But I mean, we will see this throughout. I mean, we will see this throughout discussing the individual problems. I mean, I'll tell you actually exactly what I will use as the initial state. Was there another question?
I have a question. In your generating functional,
yes.
So you put two sources, right? J and R.
Yes.
So why did you put R also along with J?
Very good question. That will be answered next week.
Okay.
The reason is that later I will perform Legendre transformations, and I want to perform a Legendre transformation with respect to R as well. At the moment, you can just set R to 0, right? Okay. But I just wanted to introduce. I didn't want to introduce this object twice. Okay.
Okay. Thanks.
Okay. So now we have 10 minutes left, but I kind of wanted to make this a little bit more explicit, and then somehow start to discuss one physical example. Okay. Yeah. So one physical example of what you can actually now do with this classical field approximation, how this actually works out. Yeah? So now we have, so we constructed this path integral, right? Okay, we found an approximation where we can actually calculate something, right? So, next thing you do is you go out and calculate, okay? So let's try to calculate something, right? And so for the moment, we haven't really talked about what the correction guys are, right? So let's be very careful. Let's try to apply this method of classical statistical field theory to a problem where we actually know it's going to work. Okay, and so the example that I'd like to consider here in the last 10 minutes is that of critical dynamics of a scalar field. Okay, so what are we going to do? So we're going to look again at our classical scalar field, our old friend here, right? But now what we're going to do is we're going to choose our microscopic parameters such that we make the mass that appears in the potential of the field, we're going to make that negative, okay? And then what will happen is that this dimension larger or equal than 2, this model will have a second order phase transition at a finite temperature. So what does that mean in practice, right? So in practice that means that if I'm at low temperature, okay, then somehow this field will sit essentially I have this double wave potential, right? And the field will somehow sit in one of the minima, and I can single them out by somehow introducing a small bias and then taking the thermodynamic limit. So below the critical temperature, the expectation value of the field, okay, will be non-vanishing, right? And so then above the critical temperature, it will be 0 again, right? So where essentially fluctuations modify this effective potential and the symmetry is restored, okay? This is a second order phase transition in this model, and okay, this is actually important because near a second order phase transition, the physics is universal, okay? And so that's how I'm going to exploit here using a classical theory to potentially describe something that is actually maybe of interest in quantum theory, right? Exploiting essentially the universality between these two things. Okay? So this is roughly speaking the phase diagram of this model here. Yeah? So we have this kind of symmetry breaking parameter, which I call J, right? And so, okay, there's a second order phase transition here at a finite temperature and zero explicit symmetry breaking. And so what happens in the vicinity of this second order phase transition is that the system starts to feature long-range correlations. The spatial correlation length diverges. I mean, these are things that you guys are familiar with. I'm iterating them here anyway, right? And so near the critical point, somehow the macroscopic properties of the system are governed by universal scaling laws. For instance, the correlation length diverges as this critical exponent mu, right? The order parameter of the transition goes to 0 with a certain power law, which is given by beta. Yeah? And so the important thing is here that these properties are really universal in the sense that somehow these, for instance, these critical exponents, alpha, beta, gamma, delta, nu, eta, they're identical for different microscopic realizations of the systems within certain universality classes. Now, this is somehow static behavior, right? And so these static universality classes, they're governed by very few things, such as dimensionality of the system, right? So let's say we are in 2D, for instance, right? And the symmetry breaking patterns, so what symmetry do I actually break? So in this case, I just have this kind of reflection symmetry in the potential, so it's discrete Z2 symmetry. So this is in the Ising universality class. Okay, now that's not really what we're interested in, right? I mean, to study somehow static equilibrium properties, right? I wouldn't have to talk about dynamics, right? So really, what is more interesting to look at is somehow the dynamics in the vicinity of critical point. And so in that context, it turns out that actually there's also some very interesting things going on related to this phenomenon of critical slowing down. So what is this critical slowing down? So what this critical slowing down tells you that not only somehow your spatial correlation length diverges in the vicinity of the critical point, but also somehow the time scales, the autocorrelation times in the system, they also blow up once you approach this critical point. And so maybe perhaps an intuitive way to think about this is, so this is some snapshot I took from a Java applet of our Ising model simulation, is that near the critical point, you somehow have these very long-range ordered clusters, right? And so these are correlated, of course, over long time scales, because it somehow takes a very long time to somehow communicate information to these arbitrarily large clusters. And so that's essentially somehow intuitive picture for why also the temporal correlation, so the temporal correlation length, so the autocorrelation time also diverges. Now, it turns out that this is that again, so this divergence of this autocorrelation time is also governed by a critical exponent, but this is now not like the static critical exponents that you may be familiar, but it's a dynamical critical exponent, which is called Z. And so Z basically characterizes, how strong the divergence of the temporal correlation length is compared to the spatial. Now, what is interesting about this is that, of course, now you're talking about dynamics, right? Before we were talking about statics, right? So in statics, we know we have these kind of large universality classes. They only depend, say, on the dimension of the system and symmetry breaking patterns, right? But now you're talking about dynamics, right? And you're talking about dynamics on long time scales, right? So natural question that you have to ask yourself is, somehow what can dynamics on long time scales be affected by? Is it only affected by dimensionality and symmetry? Not really, right? There's other things that can come into play. And so things such as, for instance, conservation laws are extremely important in actually determining somehow the long-term dynamics of system, okay? Right? And so it turns out that actually for critical dynamics, there are again universality classes. These are called dynamic universality classes, and this goes back to classified in a scheme by Halperin and Hohenberg. But it turns out that, okay, so you have to now take into account these somehow additional quantities, such as how do conservation laws affect the dynamics of the system. And essentially, what happens is that sort of for different models in a given static universality class, they can have different dynamics. And so your static universality classes, they basically can split into different dynamical universality classes. For instance, systems which don't have any conserved quantities, they're called model A. Systems which have a conserved Quark parameter are called model B. Systems which have some kind of energy momentum conservation are called model C, and the list goes on and on. Okay? Now, I'm not going to finish this, but let me say what the essence of what we're going to do on Monday then is, right? So the essence is here somehow in the top line, and that's only one thing I wanted to focus about. The point is that, okay, for this particular example, in principle, I didn't need a discussion of non-equilibrium quantum field theory, right? But what I certainly know is that if there are no quantum anomalies, and in this scalar theory there are no quantum anomalies, okay, then certainly the symmetries and the conserved quantities are the same for my classical field theory as they are for my quantum field. And so what that means is that I can actually go and somehow study these universal properties in the vicinity of a second-order phase transition simply using this classical statistical field approach. Okay? And that's what we're going to do next. Thanks.
Okay, thank you very much for a definitely very interesting talk. Are there any questions? Yeah.
Hello. I have one confusion. So in the Keldy-Schwinger contour,
the contour, yes.
You have two sets of field. One is the right movers and the left movers. I mean, the top are
which one? Which slide?
Keldy-Schwinger contour, right?
Yeah.
C plus and C minus. So in the upper contour, the path order is equivalent to the time ordered, but in the lower contour, path order is anti-time ordered.
Exactly.
So in quantum field theory, whenever we talk about correlation function, it is always a time ordered correlation function. So in the so if I want to define a green function, which is the time ordered correlation function of two scalar field, then in the upper line I can always define it, but how one defines the green function in the lower line?
Excellent point. Actually, what you do is, okay, so when you actually compute this, right, and you say you do this with the generating functional that I introduced, right? If you want to have the time, so what I disagree with in your statement is that we only care about time-ordered Green's function. That's simply not true. Yeah? In principle, we care about more than that, right? These are just usually the objects that we have the most easy access to, okay? Yeah? So what you do is, if you want to have a time-ordered Green's function, okay, then you simply evaluate your field correlator on the upper branch of the contour. Yeah? Whereas if you want to have definite time ordering, for instance, right, or definite, not definite time ordering, definite operator ordering, say you want to always have phi 1 to the left of phi 2 or something like this, then you put phi 1 here and phi 2 here. Because then you always know this guy will come after this guy. Because that's the operator ordering that obeys. Okay?
So in this case, it is also, I mean, this also means a Green's function, or it has a different meaning?
No, it also means a Green's function, yeah. I mean, so look, right? I mean, so if you talk about two-point correlation functions of quantum mechanical operators, you can essentially distinguish two different objects, right? You can either say, okay, I put my one operator here and my other operator here, or I invert the order. Or I can say I make them time-ordered and anti-time ordered. Or, I mean, these are all the points, I mean, right? There's different bases to somehow formulate the possibilities. But in principle, there are two independent Green's functions. And actually what you need to really describe somehow what's going on, you actually need both of them in non-equilibrium. In equilibrium, they're actually related.
Further questions? If not, then let's thank the speaker again.